Hello, my name is Daniel Ifko and welcome to my presentation. Today, I'll be talking about the theme of safety. What do we think when we think of the word safety? One might think of its normal dictionary definition of the condition of being protected from or unlikely to cause danger, risk, or injury. Now, of course, this is the only way one can look at the definition of this word. It is making a safe environment for people. But as this is an ethics and philosophy course, we must dive deeper into just the word safety. We must dive into the actual surroundings of safety, such as products that are created by people. We must ask, how safe is this thing for the consumer and people around it? What will consequences be if something goes wrong? How much do we have to focus on safety? Should we focus on the safety of people using the technology, or the safety of people controlling the technology within? These are all questions that are important to every engineer in the world when creating something. Of course, we must evaluate these questions in something physical. Today, I'll be looking into, talking about, and breaking down 4 nuclear disasters and the reason why these occurred, and other things that are important and relate to the moral ethics of safety. I will go through all 4 one by one and then compare them at the end. For the first and main case that I believe we are all familiar with is the largest one on the list, and that is Chernobyl. Of course, we all know or have heard about this story, and we all know the great danger and permanent harm that has occurred because of this. However, let's start with the history of what happened. The Chernobyl disaster was a nuclear accident that occurred at Chernobyl nuclear power plant on April 26, 1986. A nuclear meltdown in one of the reactors caused a fire that sent a plume of radioactive fallout that eventually spread all over Europe. Chernobyl nuclear power plant, built at the banks of the Pripyat River of Ukraine, had 4 reactors each capable of producing 1,000 megawatts of electric power. On the evening of April 26, 1986, a group of engineers planned an electrical experiment on the number 4 reactor. With their little knowledge on nuclear physics, they thought of experimenting how long a turbine would spin and supply power to the main circulating pumps following a loss of main electrical power. Due to the misconception that this experiment belongs to the non-nuclear part of the power plant, it was carried out without proper exchange of information between the testing department and the safety department. Hence, the test started with inadequate safety precautions, and the operating personnel were not alerted to the nuclear safety implications of the electronic test and its potential danger. According to the test plan, the emergency core cooling system of the reactor, which provides water for cooling the reactor core, was shut down deliberately. For the test to be conducted, the reactor had to be stabilized at about 700 to 1,000 megawatts prior to the shutdown, but it fell down to 5,000 megawatts due to some operational phenomena. Later, the operator working in the night shift committed an error by inserting the reactor control rod so far. This caused the reactor to go into a near shutdown state, dropping the power output to around 30 megawatts. Since this low power was not sufficient to make the test and will make the reactor unstable, it was decided to restore the power by extracting the control rods, which made the power stabilize at 200 megawatts. This was actually a violation of a safety law due to the positive void coefficient of the reactor. A positive void coefficient is the increasing number of reactivity in a reactor that changes into steam. The test was decided to be carried out at this power level. In actuality, the reactors were highly unstable at the low power level, primarily owing to the control rod design and the positive void coefficient factors that accelerated nuclear chain reaction and the power output if the reactors lost cooling water. At 1:23, the engineers continued with their experiment and shut down the turbine engine to see if its inertial spinning would power the reactor's water pump. In fact, it did not adequately power the water pumps, and without the cooling water, the power level in the reactor got surged. The water pumps started pumping water at a slower rate, and they, together with the entry to the core of the slightly warmer feed water, may have caused boiling at the bottom of the core. This, along with the xenon burnout, might have increased the power level at the core. The power level was then increased to 530 megawatts and continued to rise. The fuel elements were ruptured and led to steam generation, which increased the positive void coefficient, resulting in a higher power output. The high power output alarmed the engineers, who tried to insert all the 200 control rods, which is a conventional procedure done in order to control the core temperature, but these rods got blocked halfway because of their graphite tip design. So before the control rods with their 5-meter absorbent material could penetrate the core, 200 graphite tips simultaneously were dropped, not being able to reach the core, which facilitated the reaction to increase, causing an explosion that blew off the 1,000-ton heavy steel and concrete lid off of the reactor, consequently jamming the control rods halfway. As the channel pipes began to rupture, mass steam generation occurred as a result of depressurization of the reactor's cooling circuit. As a result, 2 explosions were reported. The first one was the initial steam explosion. Eventually, after 2 to 3 seconds, a second explosion took place, which could possibly be from the buildup of hydrogen due to the zirconium steam reactions. All of the materials such as fuel, moderators, and structural materials were ejected, starting a number of fires, and the destroyed core was exposed to the atmosphere. In the explosion and ensuing fire, more than 50 tons of radioactive material were released into the atmosphere, where it was carried out by air currents. This was 400 times the amount of radioactive materials released at the time of the Hiroshima bombing. The Chernobyl power plant disaster in Ukraine is the only accident in the history of commercial nuclear power to cause fatalities from radiation at the time. There are many fatal effects due to the radiation released, and a few of them go as follow. 2 workers had died. One immediately got burned to ashes after the accident, while the other was declared dead at the hospital within a few hours of admission. 28 emergency workers and staff died within 4 months of the accident due to thermal burns and the radiation effect on their body. This accident created 7,000 cases of thyroid cancer. Acute radiation syndrome, or ARS, was diagnosed in 237 people who were on site and involved in cleaning up. The land, air, and groundwater were all contaminated to a great extent. The direct and indirect exposure to radiation led to several health problems such as Down syndrome, chromal aberrations, mutations, leukemia, thyroid cancer, and congenital malfunctions, and a number of plants and animals faced destruction as an after effect. We know now after all the reports that the cause of the explosion was miscommunication, lack of safety procedures, negligence, and unqualified staff. As for placing responsibility, we cannot really point it anywhere except at the group of management, operators, and engineers. Now, because this is ethics, we must look at the events leading up to the incidents, which we already talked about, how it was handled, and how it is still being handled. During the accident, they turned off all safety systems to perform a safety test. Firemen were never taught how to cope with the situation, and they ignored original designs. The Soviets tried to cover up the accidents, which they hastily built a sarcophagus for the plant, and it was built in dangerous conditions. Because of this, the outcome was the World Association of Nuclear Operators. Reactors similar to Chernobyl were improved, RBM cane designs were altered, and most importantly, more caution with nuclear power. Now, 7% of Ukraine's budget goes to cleaning up and repayment for Chernobyl, and the US is funding new containment structures. Worst of all, Chernobyl's area is radioactive for at least another 1,000 years. This accident is something that we should point directly to utilitarianism. It seems that is why someone, despite prevail of utilitarian ethics in disaster, believes that virtue ethics and self-sacrifice could help us in very difficult circumstances. During the cleanup process, what extent is the risk that care providers could accept during disaster? According to the utilitarian ethics, we must balance between risk and benefits of care that could be provided. It is based on the proportionality principle. Unfortunately, it isn't possible to determine a sharp and exact border between ethically acceptable and non-acceptable duty in disaster. Along with the coordination, the control rod of the power plant was designed in a very disoriented way for the cooling that went along with it. The Chernobyl plant did not have the fortified containment structure common to most nuclear power plants elsewhere in the world. Without this protection, radioactive material escaped into the environment. The next nuclear accident is a recent one and very close to home if you live anywhere on the east side of the USA, and that is the 3 Mile Island case in Pennsylvania. The 3 Mile Island power station is near Harrisburg, Pennsylvania, and it had 2 pressurized water reactors. TMI-1 entered service in 1974 and still operates safely. TMI-2 was brand new when the accident occurred. At 36 seconds past 4 a.m. on the 28th of March 1979, the first series of pumps feeding water to the steam generators at the 3 Mile Island nuclear plant stopped functioning. It was later determined that this was caused by the maintenance work being done on the number 7 polisher at the time. The steam produced by the reactor not only runs the generators to produce electricity, but also serves to cool down the reactor core, reducing the risk of a meltdown. When the flow of the water stopped, the temperature inside the reactor core increased. This caused the water inside the reactor to expand, increasing to 2,200 psi, 100 psi more than normal. As designed, the increase in pressure caused the pilot operator relief valve to open, draining the steam and the water from the reactor core into a tank on the floor. At this point, the 3 emergency feed water pumps started, but an operator noticed that they were running, but did not notice that the feed water lines were closed, and the control panel had no light to indicate this. Despite the opening of the PORV, the pressure continued to rise. 9 seconds into the accident, the control rods automatically lowered as designed to halt the fission reaction. This halted the fission reaction, but the latent heat of the radioactive material continued to heat up the water. Even though this heat was a fraction of what is normally produced during the fission reaction, it was enough to potentially overheat the core. 13 seconds into the accident, the PORV should have closed since the pressure in the reactor had dropped. The light indicating that the PORV was energized shut off, leading the operators to assume that the PORV has now closed. In reality, the PORV was stuck open and the steam and water was escaping from the reactor. This is known as a loss of coolant accident. In the first 100 minutes of the accident, almost 32,000 gallons of water, or 1/3 of the reactor's capacity, escaped through the PORV. The accident at TMI could have been contained had either the PORV shut at its point or the operators noticed that the valve was stuck. During the initial stages of the accident, Edward Frederick and Craig Faust and the control room operators were present in the control room. One of the factors that added to the severity of the accident at TMI was the inadequate training of employees at the facility. Over 100 alarms went off in the control room during the first few minutes of the accident. This added to the confusion without providing any useful information to the operators. Both Faust and Frederick dealt with the alarms to the best of their ability based on the training they had received. 2 minutes into the accident, the pressure of the water in the reactor dropped sharply, which caused the emergency injection water to be automatically activated. This sent about 1,000 gallons of water per minute into the reactor's cooling system. The falling pressure coupled with the constant reactor cooling temperature should have alerted the operators to the LOCA. Instead, fearing that the core would have too much water, Operator Frederick turned off one of the EOI pumps, reducing the flow of water to the core to less than 100 gallons per minute. 8 minutes into the accident, it was discovered that the emergency feed water was not reaching the core because of the closed valves. Operator Faust proceeded to open these valves, allowing the water to rush into the steam generators. It was later discovered that these valves were closed 2 days earlier during a routine test of the pumps. At 4:11 a.m., an alarm signaled high water in the containment building. This is the building where all the water drained from the core through the PORV is stored. In itself, this alarm should have been a clear indication of a leak in the cooling system. When Frederick was informed of this, he recommended that the sump pump drained water to the containment building be shut off. By about 6:15 a.m., roughly 2 hours and 15 minutes into the accident, the level of water in the reactor had dropped below the level of the core. Unknown to the operator, the core is now uncovered. It is always essential that the core remain covered to prevent it from overheating. Once the core overheats, the zirconium alloy of the fuel rod cladding reacts with the steam to produce hydrogen gas. This is what happened in the TMI reactor. Not only is the hydrogen produced flammable, but the diminishment of the fuel rod's cladding increased the risk of radioactive containment. Since the core was out in the open, it started spewing radioactive smoke into the cooling pillars. It took 12 years and cost $973 million to decontaminate to low levels of radiation. There were 10.6 megaliters of radioactive coolant that were processed, stored, and safely evaporated. About 100 tons of damaged radioactive fuel was put into 342 canisters. They were shipped to the Idaho National Laboratory and stored in concrete containers. One thing we see that is like Chernobyl is the lack of people who understand what they are doing, and not only that, but the communication failure. This case was also a bad form of decision-making under the conditions of uncertainty, communication, and coordination in intergovernmental action, public safety versus efficiency in management risking technology, and the community's right to know versus responsible management of information in crises. These violate almost all the engineering code of ethics, mainly the first and third one, which says that hold paramount the safety, health, and welfare of the public, and issue public statements only in an objective and truthful manner. The public was hidden and misinformed after and during the accident. Another one which can be argumentative is that the 3 Mile Island violated the second fundamental canons, which says perform services only in areas of their competence. 3 Mile Island was very populated and any accident would have been devastating, but one can be devil's advocate and say that nuclear power is safe under good hands. 3 Mile Island is an example of an ethical disaster, but thankfully was cleaned up very well and quickly and safely. Another very major but small nuclear accident was the Tokamura nuclear accident in Ibaraka Prefecture, Japan. At approximately 10:35 a.m. on September 30th, 1999, workers at the JCO nuclear fuel processing plant poured a 7th batch of 18.8 enriched uranyl nitrate solution along with uranium-235 into a precipitation vessel. The goal of this process is to convert the isotypically enriched uranium hexafluoride into uranium dioxide fuel. However, the addition of the 7th batch of solution caused a self-sustaining chain reaction, otherwise known as criticality, that persisted for several hours. Once the nitric acid solution was added to the uranium, the criticality began. Neutrons and gamma rays were emitted and led to eventual deaths of the worker Hirashi Ochu and Masato Shinohara. The reaction was difficult to stop due to the fact that the uranium was already mixed within the solution, providing no way for the workers to prevent more nuclear fission reactions from occurring. It was only until the cool water vessel was drained, which enriched the precipitation vessel and acted as a neutron deflector, that workers were able to cease the criticality. In addition to the death of the 2 workers, at least 439 people, including plant workers, firemen, and others who responded to the accident, as well as 207 local residents, were exposed to elevated levels of radiation. Yet the criticality event that changed the course of Japan's nuclear history could have been avoided. The criticality's occurrence resulted primarily from misunderstanding the chemical processes, safety procedure, and a miscommunication from risk management to the chemical engineers involved. Since the plant had not been operational in the 3 years prior to the criticality, proper guidelines were not put in place to prevent such an occurrence. At its core, the criticality is attributed to what the Japanese called kaizen, which means improvement, carrying the connotation in industry to enhance workplace operations and the environment. So this drive, cultivated by the top management, not only led to inadequate risk awareness, but the overall Tokamura accident that shifted Japanese nuclear in the opposite direction. It is a common understanding that public opinion has played little to no role in Japan's policy formation in relation to other democratic states. Yet in light of the criticality accident of 1999, the Japanese government produced a variety of new laws and institutional changes to address safety concerns to ensure events like this were prevented in the future. As we know, Japan has continued to suffer from the use of nuclear power, such as the tsunami that wreaked havoc on the plants at Fukushima, and has adjusted its use of the powerful but unstoppable power source accordingly. 3 workers received lethal doses and died as a result of the accident, despite advanced medical treatment and attempts to save them. It is 140 kilometers north of Tokyo, but a total of 119 people received the radiation dose of over 1 Servian from the accident there. There was a local evacuation of some households and others were told to stay inside until it was safe. The cause of the accident was workers mixing too much uranium containing water into buckets, reaching a critical level for a chain reaction to start and giving lethal doses to those 3. They not only had been trained well, and the IAEA reported placing the blame on human error and serious breach of safety principles. However, another more dangerous ethical violation is that the company conceded that it violated both normal safety standards and legal requirements, and criminal charges were laid. The 3 workers concerned were hospitalized, 2 in a critical condition. 1 died 12 weeks later, another 7 months later. The 3 had apparently received full-body radiation doses from mainly the neutrons of about 16 to 20,000 millisieverts. About 8,000 millisieverts is normally a fatal dose. Another 24 JCO workers received up to 48 millisieverts. Doses for 436 people were evaluated, 140 based on measurement and 296 on estimated values. None exceeded 50 millisieverts, although 56 plant workers exposed accidentally ranged up to 23 millisieverts, and a further 21 workers received elevated doses when draining the precipitation tanks. 7 workers immediately outside the plant received doses estimating at 6 to 15 millisieverts. Although this might sound complicated, in simpler form, during the cleanup process the workers were exposed to extreme level of radiation without knowledge. This once again is a pure violation of the Code of Ethics for Engineers. Not only did they lie about the radiation levels to workers, but they also did unsafe actions and knew what they were doing wrong. They essentially broke all 6 rules in the first section of the fundamental canons in the Code of Ethics for Engineers. This also was a violation of the justice ethical principle, which states that the decision makers should focus on actions that are fair to those involved. Now, to end on a more positive experience somewhat, we will talk about the Windscale Fire, or the British atomic bomb project in Cumberland, UK. The Windscale Fire of 1957 marked Great Britain's largest nuclear disaster, ranking at level 5 classification on the International Nuclear Event Scale. During World War II, the Manhattan Project, as a defense against Germany, ignited the United Kingdom's involvement in nuclear fission as a military weapon. The Manhattan Project was a collaborative effort from the United States, United Kingdom, and Canada. When World War II ended, the United States closed their nuclear weapon program to other countries. In an attempt to maintain their position as a world power, the United Kingdom expedited their research and technology to build their own nuclear weapon project. Thus, in 4 short years, 2 wind-scale piles were built in Cumbria, New England. Each pile was housed separately in large concrete buildings a couple hundred feet apart. Additionally, they were fueled by 180 tons of uranium metal. The reactors manufactured plutonium used for nuclear weapons, as well as the polymonium and tritium used for fission triggers. On October 7, 1957, a routine heating of the wind-scale Pile 1 began, using the Wigner approach of annealing the reactor core. Next, the power was increased to further raise the temperature. However, instead of a gradual release of energy, the high temperature caused the build-up energy to be stored in the core. In hopes of accelerating the Wigner process, the operators increased the power even more. Due to the poor placement of the Reactor 1's thermometer, the operator could not get a read at the core's highest temperature, causing the operators to be unaware of the dangerously high temperature. This led to the temperature to exceed a maximum of 400 Celsius. On the morning of October 10th, operators noticed the extreme condition and proceed to venture to the charge face in protective gear to secure the inspection plug. By this point, the operators detected the fuel channels a bright red that soon turned into flames, scorching the graphite and the metal aluminum casing around the rods. In an attempt to fix the situation, the operators turned the cooling fans to high. Instead of extinguishing the fire, this only fanned the flames. At this point, 21 out of 53 channels were filled with fires. Efforts to discharge the burning cartridges into the water ducts were unsuccessful. Operators continued their attempts to diminish the flame with liquid carbon dioxide. Finally, shutdown fans were turned off and the water slowly doused away the flames. At around 3 p.m., the water was turned off after the fires completely subsided and the reactors were cold. No one in the area, despite the release of radioactive containment, was affected. Filters on the top of the piles prevented some radiation from escaping. Shortly following the disaster, an investigation took place over the next 10 days. Scientists immediately came up with the 3 possible causes of the fire: the graphite itself, a burst uranium cartridge, or a titanium cartridge. Upon further investigation, they concluded that the real issue was human error. The operators made a fatal mistake when performing the Wigner energy method. This process, discovered by Hungarian physicist Eugene Wigner, was a cycle of controlled heating called annealing cycle to capture the energy inside the reactor. This controlled heating proved successful and was deemed safe if done correctly. However, the operators that caused the wind-scale fire failed to acknowledge that the temperature was dropping as it should. Thus, the second heating should have never occurred. Additionally, the operators increased airflow on both October 8th and October 10th in response to the temperature rise. Instead of proceeding into the next phase in the controlled heating, it only fanned the flames. The Wigner energy method is a process that is taken on case by case. Furthermore, it is a complicated process that was left in the hands of junior staff who lacked the proper knowledge and training to handle any unforeseen situations, such as the overheating that occurred. Additionally, the thermometers were not placed in the accurate place to measure the heat at its highest temperature. Later, researchers found out that 2 thermometers were not even working properly. Now, although there were a few problems with things such as non-working products and inaccurate products and not enough training, the people who built the site were smart enough to cover up all exit points where any radiation can come out of, which in this case was a chimney. If that chimney had not been covered, there would have been a lot of radiation seeping out all over the countryside of England. Now, let's talk about the conclusion. Throughout all of these accidents, we all see a similar pattern. The accidents always happen due to one of 3 things: lack of personal safety, lack of engineering safety, and a lack of qualified individuals. Throughout all of these, we can see this very clearly. Let me talk about the ethics that show within these benefits. One common one is utilitarianism. Utilitarianism is the act of basing one's own ability to predict the consequences of an action, more specifically, act utilitarianism. To a utilitarian, the choice that yields the greatest benefit to the most people is the one that is ethically correct. Now, of course, nuclear power creates a great amount of electricity to a large area. This, of course, would benefit many people in smaller countries. It benefits the greater good for most people. However, it can also contradict itself. If you make a nuclear power plant close to homes and a city like the 3 Mile Island case, then you will have the issue with making a very dangerous situation if even a small thing goes wrong. This also is like the ethical principles of benefice, which is the principle that guides the decision maker to do what is right and good. Now in the case of Chernobyl, we almost saw a selfish desire in the incidents. The leaders knew that the reactor was a low power and that there was no proper coordination or the communication and kept going with it. Along with that, we saw multiple safety designs that were present. We see a pattern that is all in the other nuclear disasters we talked about. There was either bad communication or bad safety design. Now that we are done with the specifics, I wish to talk about the general ethics of nuclear energy. The ethical issues of nuclear energy focus on the comparison between the benefits and the hazards of nuclear power, the catastrophic impact of nuclear accidents, fact disclosure, and safety regulations and violations. These issues have a great effect on global health. When it comes to impact on environment, there are pros and cons on this aspect. On one hand, nuclear energy is sustainable, does not emit greenhouse gases, and generates far less waste than the conventional energy. With increased demand for energy and diminishing fossil fuel supply, nuclear energy, a sustainable alternative, seems feasible of an option to replace fossil fuel. Opposingly, nuclear energy is not green. It involves mining and refining of radioactive raw materials and disposal of radioactive wastes, which can damage the environment and bring health risks to nearby residents. As mentioned previously, nuclear power requires mining, enrichment, transport, and disposal of radioactive materials, and many nuclear power plants locate in densely populated areas. Residents near these activities are put under the increased risk of cancer and other health problems due to long-term exposure to low-level radioactivity. A nuclear accident will elevate such risk to another threshold. This is against the principles of no malefice and justice. Nuclear waste are now stored temporarily at each nuclear power plant site, which increases the risk to nearby communities and may have potential security risks. So far, there is no permanent solution on nuclear waste disposal. Another very important one is fact disclosure. Full disclosure on potential risks, prompt information sharing, and training on self-help methods could help save lives, reduce injuries, and smooth public panic, particularly in the case of nuclear accidents. In contrast, governments and industries often downplay the potential risks or do not release the full facts to the public. The only ethical way to address public concerns is to release accurate and objective information to the public in a timely fashion. In order to resolve the ethical issues, nuclear power regulators and industry should follow the ethical values and principles to make decisions in order to maximize the benefits and minimize the harm. Different stakeholders may have different opinions on nuclear energy due to the different values and principles, different facts and informations they have on nuclear energy, and different perceptions on the outcome of the decision. In addition, development in science and technology could change the ethical issues. In the Western world, utilitarianism is a dominating theory that values the maximal well-being for most people. If one applies the utilitarianism view to the nuclear energy program, the key questions are: does the nuclear energy program maximize the well-being to most people, and are there alternative options to accomplish the same outcome? The proponents of nuclear energy, including many governments around the world and international organizations, emphasize that the nuclear energy is sustainable, clean, and generally safe, thus should be developed to replace fossil fuel energy. They contend that the accidents are isolated cases that should not dissuade mankind from using nuclear energy. They contest that the public overreact about the damaging effects of nuclear accidents. Therefore, the governments often assure the public that nuclear power is clean and safe. They emphasize that the safety of nuclear technology has improved significantly in the past several decades. Based on the ethical principles of utilitarianism, non-maleficence, beneficence, justice, disclosure, and autonomy, the following changes are proposed. Improve the safety standards of nuclear technology to minimize the harm to the environment and global health by implementing more stringent safety checks and review measures by decommissioning aging plants and those that fail to address safety concerns. Enforce safety regulations to ensure full compliance, shut down the plants with identified safety risks, and hold the persons responsible. Mandate the sharing of timely, accurate, clear, and credible information with the public in order to reduce the damage done to radiation emergency and maintaining high public trust and confidence. enhance international coordination between government and international organizations and industry on guidance, regulations, law enforcement, radiation monitoring, and follow-up on potentially affecting populations. And lastly, integrate medical care and psychophysical support for high-risk populations after nuclear accidents to help reduce the psychological damage to the public. While nuclear energy is regarded as a sustainable energy that helps greenhouse gas reduction, it generates highly toxic radioactive waste, irreversibly damages the environment and public health. Any nuclear accident has a far-reaching impact on global health. Based on the ethical principles of utilitarianism, non-maleficence, benefits, justice, disclosure, and autonomy, authorities and nuclear industry need to make more stringent approach on nuclear programs, improve nuclear safety, enhance risk management, require full disclosure and open communication to the public, and develop alternatively green energy such as wind, solar, and geothermal energy. Thank you for watching my presentation.